Watch the video from the last time. Do you have any question? No, sir. Okay, then let's move on. Today we're going to look at power. How is the power delivery to the load is affected by the transmission line? When the length of the circuit is more than 1/10 of the lambda, then it's a transmission line, right? So transmission line with a generator. The generator has a source impedance. The G stands for generator, or you also can say source. Source for RF or microwave signal. And this source is connected to a transmission line. The transmission line now is connected to the load. This is V in, the input voltage. There's a difference between VG and V in. Then the input impedance, you can call this looking into the transmission line, Z in. And then you have a current flowing in called I in. Then here, you have the characteristics impedance of the transmission line, and beta is called the propagation, it's called the phase constant. The beta here is the phase constant. There's an expression for the input impedance. The input impedance is Z0 multiplied by 1 plus the reflection coefficient. Okay, this is a reflection coefficient of the load. You can write this, the reflection coefficient looking into the load. Reflection coefficient. Reflection coefficient looking into the load multiplied by E to the power of 2j beta L. One minus divided by 1 minus divided by Z0 tangent beta L. Okay, so you know all these things from the last time, maybe if you forgot. And this is the reflection coefficient at the load, and this is the phase constant. Phase constant, it gives the phase of the signal along the transmission line at a constant time. It's usually measured in radians, meter, or degree per meter. And this Z0 is the characteristics impedance of the transmission line. We talked about it, remember the last time? So this is the formula for the input impedance. If your piece of wire happens to be a transmission line. Characteristics impedance, you know, right? Last time, remember, you guys went to the microwave lab, and then you saw the network analyzer, and it was written here 50 ohms. Okay, that means since this equipment is a 50 ohms equipment, therefore you need to connect a cable that is also a cable that has a characteristics impedance of 50 ohms. If you connect a cable here, and this cables also must have 50 ohms. All must be 50 ohms. So any device that you connect to the cable also must have input impedance, output impedance 50 ohms. They all are matched. If that is the case, then there will be no reflection. Okay, there's no transmission line for low frequency circuit, and then we assume a length of the transmission line is 0 because we don't care about the length of the transmission line. There's no characteristics impedance for the length of the cable that is connecting the generator to the load. In this case, see what happens to this formula. Then this part here is going to be 0. And this part also is going to be 0. Tangent of 0 is also 0. So you're going to end up getting Z in is Z naught ZL divided by Z naught. Okay, the other part all goes to 0. So you're going to get ZL, simply ZL. So this is for low frequency circuit. So the input impedance is simply ZL. Okay, the transmission line effect, the effect of the transmission line is not included when you assume length is 0. That's what we assume for low frequency circuit. We assume the length is short. The signal that you put in, it's going to instantly going to the load. Any questions on this?
No, sir.
Okay.
No, sir.
If you look at the transmission line, the gammas of S is the reflection coefficient at the source, or source reflection coefficient. Or you can also call this the generator reflection coefficient. And this one here is called gammas of in, is called the input reflection coefficient. And this part here, see, they're all happening at the end of the transmission line, at the input and output. This is called gammas of L. It's already drawn there. So I'm going to delete this and put it red in color. So it's a load reflection coefficient. And this is called output reflection coefficient. So these are the reflection coefficient that we have to consider when trying to find out the power that is delivered to the load. If your line is not matched to the load, you're going to have a non-zero load reflection coefficient. Okay, if the output is not matched to the, if you're looking into the output, and if this output impedance is not matched to the load impedance, then you're going to get a reflection coefficient that is non-zero. Similarly, when the input impedance is not matched to the line, you're going to get a non-zero input reflection coefficient. And also here, if you can call this G, or it doesn't matter, you also can call this G. Some people call this Z of S. Some will call ZG. In this case, if we call this G, then it's G. So any questions so far?
No, sir.
So once we do an example, everything becomes very clear to you. The power delivered to the load can be affected by many things. Like for example, let's say the line is matched to the load, but the source impedance is not, the generator impedance is not matched to the line. Then the power delivered will be different. Or the other way around, this source impedance can be matched to the line, but not the load. Load is not matched to the line impedance. Then you're going to get another kind of different power that's delivered to the load. If all of them are matched very well, then it's going to be different power. There's each one of them power has a different formula, but I'm not going to be looking into all these things and confuse you guys. But we're only going to look at one thing. We're going to look at conjugate matching. You guys know what is conjugate matching? You remember? Prakash. Conjugate matching is for maximum power transfer. let's say if this is the generator ZG, and if I input impedance of the circuit, if I draw it as a load, for example, you go back to the circuit, if I replace the whole thing here, if I replace the whole thing with Z in, okay? I'm replacing everything there with Z in. Conjugate matching means when you look into the transmission line, okay, let me draw the transmission line, okay. So this is the Z in. When you look inside here, right, Z in. So I'm replacing this Z in with this load here. For conjugate matching, Z in is ZG conjugate. We can achieve this, then all the power that is available is transferred to the load, provided it's lossless.
Is that ZG or ZL? ZN is equals to ZG, is it?
ZN,
ZL,
yes,
right?
ZG, Z in. Yeah, Z in. This is, you mean this one, yeah.
Yes, no, I mean the for conjugate matching,
Uh-huh.
ZE is equals to ZG or ZL because we are replacing the ZL, right?
Yeah, this is a small g here. Okay, the load, everything is inside the Z in. It's load. Good question. Okay, so the whole, everything is inside the Z in. Like the transmission line, the impedance looking into, let's say the impedance looking inside here, this whole thing here is Z in. Everything is Z in. Did I answer your question?
Yes, sir, but my question is for, you written that for conjugate matching, Z in, right? So the Z in is equals to ZL, is it? So written as ZG.
No, Z in. Remember last time, like this is like our load right now. Okay.
Okay.
So Z in is going to be conjugate of this. So what happens, for example, if the ZG can be RG plus J XG. Okay. Z in is R in plus X in. Okay, so they have imaginary and real part. So when you make it conjugate, that means you're going to make this negative. if this is positive here, if this is positive, and this will be negative, the imaginary part will be negative. If this is positive, for example, in this case, and this is going to be negative. Conjugate means you just switch, you make sure the imaginary sign is changed for the imaginary part only. So when you do this, do you guys remember studying electronic circuit, electrical circuit last time? For example, if I want maximum power transfer, okay, talking about low frequency circuit, for example, from a circuit theory, low frequency circuit. So you have a voltage source, and then you, let's say you have 5 plus J5 as your ZG. And then I have, so now you want to find out what should be your Z load. For example, in this case, the Z in can be Z load. What should be the load for maximum power transfer? So the load should be, in this case, Z in or ZL, it should be 5 minus J5. So I'm saying here, no, ZL should be conjugate of ZG. Or in this case, if you put if we call this Z in, Z in should be conjugate of the source. If you want to get maximum power flowing to this load here, you want to have conjugate. Did I answer your question?
Yes, sir. I'm clear now. It's like adding a reactance of the same magnitude.
Okay, yes. So when you're adding the reactances cancels. So what happens now, when you add ZG, ZG plus Z in, then you get 5 plus J5 plus 5 minus J5, and then you get rid of the imaginary part. Okay, imaginary part cancel, and then you only have real part in the circuit. So only when you have a real part in the circuit, then you get maximum power transfer. A good question. Any other questions? Okay, we are not in a hurry to go through and cover as much as possible. We want to make sure, even if we cover a little bit, we want to make sure all of you have a solid knowledge of it. Guys, have any other question? So in this, in amplifier design, we are talking about conjugate matching. Conjugate matching means we are trying to cancel all the reactances and have maximum power transferred to the load. In conjugate matching, for maximum power transfer, in this case, Z in is conjugate of ZG. Or you also can write this the other way, ZG is a conjugate of Z in. Okay, if you do this, you're going to get pumping in all the available power will go in. What's available at the source, you get maximum P max going in. P max going in, but it doesn't mean that all this power will reach the load. All the power will not may not reach the load depending on the condition. If it's lossless, for example, you must consider whether it's lossless or lossless. If it's lossless, of course, there's nothing lost in the transmission line. Everything will go to the load. Another thing, you may be having a reflection here, right? You might be having reflection there. If reflection coefficient is not 0, if the line is not matched to the load, it may not be 0. And the ZG, when you go back to the circuit and see, the other coefficients like the gammas of S or gammas of G may not be 0. Gammas of G, if these things are not 0, then all this power are not going to go and reach the load. It may not be 0. Conjugate matching doesn't mean the reflection is going to be 0. They may not be 0. When we'll be doing a few examples now, and then you will see how it works. See, let's say you have a transmission line here, and then you have a transmission line here. Okay, you get the maximum power transfer, you get 10 watts going in. And then some of them going to be dissipated here if it's lossy transmission line. Let's say 1 watt is lost here. And then you come to the load, and then you will see they are mismatched. Load and line, they are not matched. Now you may get a reflection here. Maybe another 1 watt is reflected. Okay. After reflecting, some of them coming back here, and it also can get reflected at the input. Reflection going back and forth. Some of them can combine and form standing wave. Okay. So in this case, I'm just giving you a gross example here. So you have a reflection, 1 watt, for example, here. And you have, just forget about this now. You have reflection 1 watt, and then you have dissipation 1 watt. So how many watts is going to reach? Like for example, 8 watts, right? 10 minus 2. That's a very crude example. You have maximum power going in. The only way all this power can reach the load, P max will can reach the load if the transmission line is lossless and there's no other reflections. Any questions?
No, sir.
Okay, good. If no question, then let us do an example. So there's a book called POSA, where you have all the electromagnetic derivation. The author's name is POSA. There's another author, is called Ludwig. So I took these examples from there. These books are available. Writing is looking so big, okay. and load impedance if source, a lossless line with source and load with source and load impedances you have a line, transmission line. So you have this source, ZG or ZS, and then you have this load impedances, okay? And if there's no reflection, reflection 0, and there's also reflection, this reflection also 0. In this case, ZL is 0, ZG also 0. It is lossless. Then the power in, P in, power, P in means power that's available from the source. Power, okay, P in. P in, power available from the source is 1/8 VG. Sometimes I use a bigger G or smaller G. Magnitude squared over this characteristics impedance of the line. You ask me where I got this equation from. I got these equations from POSA. And it's also available in Ludwig. They have derived it. If you want to know how to derive it, then you have to take a microwave engineering. Well, VG magnitude squared. Magnitude itself is VG squared. This is the maximum available power. Okay, do you guys understand? If this is the maximum available power at the entry, right here, available power, maybe I put reflection 0, maximum available power from the source. Okay, still, even though there's no reflection, this is the maximum, this is the formula for maximum available power from the source. But all this power, is it going to get to the load? We don't know. If you call this a lossless line, yes. It's a lossless line, and if all the reflections, gammas of L and gammas of G is 0, then power P in is P load. Any question?
No.
Okay. Power in dBm. When it comes to small signals, expressing power in dBm is preferable. Let's say when you get something like, 10 to the power of minus 8 watts, 10 to the power of minus 3 watts, 10 to the power of minus 5 watts, it's difficult for your mind to see what's going on. But if you convert to dBm, you can easily see it. It's 10 log power in watts divided by 1 milliwatt. So if somebody asks you in the interview, the power is 2 milliwatt, then you are asked to find the, convert this to dBm. Okay, then all you do is 10 log P divided by 1 milliwatt. Okay, it's going to be 10 log 2 milliwatt divided by 1 milliwatt. It doesn't really have to be in watts, it can be in milliwatts also. The reason I put watts there is just to say the unit in watts. A unit in watts. 10 log 2. Log 2, how much is that? Log 2. Anybody got a calculator handy? Log 2. Log 2.
$3.01, sir.
Okay, 3.01.
3.01.
Okay, 3.01 times 10. It's all 3.01. Okay. It's 3.01, is it? So
Yes.
it's roughly around 3 dBm. 3 dBm. So that's how you calculate. Okay, this dBm is just a conversion from milliwatts or some small signals to dBm. And that's the definition of this. It's different from dB. dB is when you take the ratio of 2 power, dB. dB is when you do ratio 20. For dB in power, you use 10 log. You are given in power, dB is 10 log P2 over P1 or something, dB. If it's voltage, then 20 log V2 over V1. CT check. Any other question? Okay, guys, take a few minutes break.
Okay, sir.
Okay, sir.
You're wondering which circuit that is? That's a circuit. Let me copy that over here. Let me get rid of all the garbage. keeping only what's necessary. Z in or ZG, we use whichever. P in is the power that's entering the transmission line. So you know that this is gammas of in, gammas of L, and the rest are okay. So this is from Ludwig chapter 2. It's a lossless line. With the Z0, a characteristics impedance usually be put in the center like this, 75 ohms, or we sometimes just call this Z0, remember? 75 ohms, and then ZL is 40 ohms, and ZG is 50. So let's if this is a lossless line, we already told that this is a lossless line, right? This is a lossless line. For lossless line, with for lossless line, okay. Let's look at the case when all the reflections are zero. For reflection at the source is equal to 0, and the reflection at the load is equal to 0. This is the same formula that I mentioned earlier. Remember, for a lossless line with a source and load impedance matched to the transmission line, and this is the formula that we're supposed to use for maximum available power. Okay. For lossless line, the available power BG is 18 VG, magnitude of VG divided by the Z0, which is the characteristics impedance of the line, Z0. If it's lossless, if lossless, Z0, the line impedance is also source impedance, correct? I mean, not lossless, properly matched. maximum available power. If, sorry, I shouldn't have mentioned this. Sorry. Okay, let me repeat this again. When there's no reflection at the source, when there's no reflection at the load, the maximum available power is given by this formula. Okay, let me complete this question. Assume the length of the line is equals to lambda over 2. With a source voltage Vg is equals to 5 volts. And we are also told that it's lossless. So therefore, whatever that's available at the source can be directly transferred to the load. Do you guys agree with this? Available power is power delivered to the load. Any question? Are you guys still alive?
So far, so okay, sir.
Still live online? Okay. To find input power, we use this is the formula that I obtained from Ludwig. Pn is 1/8 Bg squared divided by Z0 1 minus squared gamma sub square divided by, right, to write this formula, 1, the magnitude of 1 minus gammas of S, gammas of L, load, e to the minus 2j beta L. And then multiplied all that by horrible formula. One minus the magnitude of gammas of L e to the minus. Actually, I don't know what I'm doing, but I'm trying my best to do something. Let's see what we are getting at the end. J beta L. Okay, the reason we need this formula, do you guys know, we already know it's lossless, right? And lossless, and we also know all the reflections are zero. But however, we know that the reflection is not going to be zero. We need this formula because the gammas of S is not equal to zero. That is because you can see gammas of S. Here I'm using gammas of S, gammas of G. So let me just change all this to G. Since I'm using G, the reflection coefficient at the source is not zero. The reflection coefficient at the source is not zero because the source impedance is not same as line impedance. And also, the reflection coefficient at the load is not going to be zero because the load impedance is not same as the line impedance. So that's why we need this formula. Another reason we need this formula, we also have a length, transmission line length. Any question?
No, sir.
Okay. Gammas of L load is equal to not equal to zero. Okay, let's look at e to the minus this guy right here. E to the minus 2j beta L is equals to e to the minus 2j beta. What is beta? Do you guys remember from last time? Beta is 2 pi over lambda. From electromagnetic class, it's a phase constant and it is 2 pi over lambda. And then we are told that transmission line length is lambda over 2. If you work that out, it's going to give you e to the minus j 2 pi. E to the minus j 2 pi is equals to, how do you guys find e to the minus j 2 pi? Do you have a calculator that can do that?
So just cross out the similar variables.
Cross out the which one?
Cross out the similar the terms, like from the, yes, correctly, from there, then cross out 2 and 2, cross out lambda and lambda, then we get 2 pi.
Yeah, so what is that equals to, the value? So if you use Euler identity, this is cosine minus 2 pi plus j sine minus 2 pi, cosine 2 pi. Sine 2 pi is always 0, isn't it? Do you remember your cosine wave, sine wave? Sine wave is always 0. At integer multiple of 2 pi, sine wave is always 0. Isn't it? You see, is always if this is 0, and this is 2 pi, and this is 4 pi, 2 pi, 4 pi. Similarly, on the side is minus 2 pi. Okay. So this is 0. What about cosine? Cosine 2 pi. We draw the cosine wave.
It's 1, sir.
Okay, so okay, we draw the cosine. This is cosine, and this is 2 pi. So by multiple of 2 pi, cosine is 1. So therefore, e to the minus j 2 pi is equals to 1. So we already evaluated that part. Now we have to evaluate the non-zero reflection coefficients. The gammas of S is Zg minus Z0 divided by Zg plus Z0. Do you remember the right? You go back to the circuit, the reflection coefficient, looking into the generator is Zg. Reflection coefficient looking into the generator is, when you look inside here, what do you see? Zg, right? Zg minus Z0 divided by Zg plus Z0. So that's how you get this. So it's going to be 50 minus 75 divided by 50 plus 75 minus 25, 1 to 5. Quite a small reflection, but it has negative sign, because now the reflection at the load, the gammas of L. Now you go here, reflection looking into the load is ZL minus Z0 divided by ZL plus Z0. ZL is 40. So once you have them all calculated, then you substitute into that formula. So it's, we are told that this is a lossless line, right? What does that mean? A lossless line means P in is P load. That means there's nothing is lost in the transmission line. Do you guys agree?
Yes, sir.
Okay. Other things like the reflection, everything, we already accounted that for. So we're using that formula, you just plug in the numbers, Vg squared divided by Z naught. And that formula, I hate to write that formula, but do we have a choice? Okay. 1 minus omegas, gammas of S multiplied gammas of L magnitude squared. Okay. So we already, this is the formula. Okay, we already know that this part is 1. Right or not? We just saw this part is 1. And this part also is 1. Plug and chug. One over 8 Vg 5 Z naught. Z naught is 75. One minus 0.2. 1 minus 0.2 minus 0.304. All that squared. This did I forget to square this? There's supposed to be a square here, right? And there's supposed to be a square here from this formula. Was there a square here? Sorry, I got this formula a little bit out. There's supposed to be a square outside here. Sorry about that. Then this square also has to be outside here. Squared, squared. One minus gammas of L square. Something is missing. Maybe I forgot to put 1 minus multiply by 1 minus gammas of L squared. So this becomes, because you are taking the magnitude, so this is become positive, right? I don't know if I'm plugging these things correctly. If there's any problem with the formula, please check this out later on. One over 24. If you guys see any mistakes, please let me know. Okay, 0.881. 1 minus, so this is 0.908. If you have a good calculator, you can calculate them out pretty quickly. 61.8 milliwatt. If you convert this to dBm, it's going to be 10 log 61.8 milliwatt divided by 1 milliwatt. So that's going to give you 17.9 dBm. Please check this formula. It's okay. I mean, the procedure is correct. But what is important is the procedure. The procedure. The procedure is quite simple. So we have the first thing to note is lossless. If it's lossless, then P in becomes P load. And then you must understand, say, once these things are not same, so therefore you're going to have reflection coefficient. You need to calculate them. Another thing to note, if you're given a length that is lambda over 2, then you have to calculate the exponential function. So this is the different thing. I just put this here. This is not related to this problem, but just want to let you know that if everything is nicely matched, then you have gammas of S0, gammas of L0. Then the power formula is quite simple. The power formula is very simple. The gammas are not there. The gammas are not there. The exponential functions are not there. Again, pointing out again, if it's lossless, please take note. The available power is the power that is delivered to the load. If you have mismatch, then you have to use this formula for mismatch. Loads and line. Then you have to use this formula. Sometimes if you see it is matched at the load, then you can put this equal to 0. Right? If you see that generator reflection coefficient is 0, it's matched very well, then you can put this to equal to 0. Sometimes both of them, one of them will be matched, the other one will be not matched. So you put a 0 accordingly. That will simplify your calculation. In this case, both are mismatched. Both the loads are not matched to the line. So therefore, both of them are not 0. So you have to use the entire formula here to calculate things. So keep this identity in your mind, how to evaluate this. You have to calculate the reflection coefficient separately and then plug them into that formula. Make sure I got this formula here correctly. Okay, guys, I have another 20 more minutes, around 20 more minutes. I can do another problem, or we can do it tomorrow, on Thursday. Which one do you guys prefer? It will also take some time to do. I think if I get started, it won't finish. It will take another half an hour. So I'm asking your permission. Should I do this the next time?
Can, sir.
Huh?
Can. We can do it on Thursday.
Okay. Do everybody agree with the leader?
Yes, agree with the leader, sir.
Okay, leader. We will continue the next time. Thank you, guys.
Thank you, sir.
Thank you so much.
Okay, bye.